I hope sound is good and everyone can see me. I shall get started now. And yes, Peter, you're right. I given many talks, so sorry to everyone. I seem to be taking up a lot of your time by giving all the talks, right? But the reason is
no problem.
Yeah. So this talk is the one that was originally planned long ago, right? So I volunteered to this talk to Peter since September or August, around there. And the other talk came because the Nobel Prize was announced for physics, and it was about black holes. So as a black hole researcher, I was obligated to give a public talk. So this is the reason why I'm giving 2 talks this semester. But aside from that, so I'm here now to talk about this particular project. And although this is a research talk, it is actually kind of the contents is actually kind of simple. And it is also a very strange and weird project to me. So for a few reasons. Number one, this project was done during the most intense periods of the MCO, March and April, around there. And the second reason is this project mainly started because of social media. So I was following a mathematician, John Bass, on Twitter, and he talks about, there was one day he was talking about hypocycloids and things, and he was showing the graphs and pictures. And when I was looking at the picture, it kind of reminded me of something I've seen before. So about 5 years ago, I was working on this Melvin magnetic universe, and the pictures I got out of that looks very similar to hypocycloid. So I was wondering those objects, whether they are exactly the same thing or it is just a visual coincidence, right? So it is something that you have to calculate and show exactly. And yeah, so I did that, and here I am to tell you about it today. So I'm going to talk to you about the hypocycloids in the Melvin universe. So today's talk consists of 4 parts. The first part is mostly should be understandable to a lot of students, and I see a lot of students in the audience today. So I'm going to tell the story about the Brachistochrome problem, and this is where cycloids and hypocycloids come in. In the second part, I will explain what do I mean when I say the Melvin spacetime or the Melvin magnetic universe, and in particular, this project is about studying the motion of charged particle in the Melvin universe. So the result that we found is that the hypocycloid occur in 2 situations: perturbed circular orbits and in the weak field regime. So these are the last 2 parts. Yeah, so let's get started. I'm going to tell the story about the Bakistochrome problem. So this is the classic problem in physics. Most students, especially physics students, those who are here, you will probably learn this in your year 2. So this is a problem that goes like this. It was originally proposed by Johann Bernoulli in the year 1696. And the question is this. So I have a particle of mass m initially at point A, and then the final position is at point B. So the only force present in this situation is gravity. So you have the conservation of energy. Conservation of energy is satisfied here. But what is the path that can be taken by the particle so that it will arrive at point B in the shortest time? So this is called the Brachistochrome problem. I believe chronos is Greek for time, and brachisto is something about the shortest time. So, but if you are familiar with the conservation of energy, you can probably understand the problem, if not yet the solution. It's like this, right? Let's say I try to move in this path. So in this path, right, I start from rest. So in this blue line, I spend most of the time having high potential, so the kinetic energy is quite low, except for the last minute. So we expect the motion is very slow here, so this will take a very long time. Okay, but we want brachistochrone, shortest time, so we want to speed up the motion. So what you can do is, okay, fine, I can try to take this direction. Right, so if I follow this path, I immediately drop potential and get a high kinetic energy. So maybe most of the time, my particle will travel faster. So can it be the shortest time? Well, if you draw this path, this is a very long distance to cover, right? If you draw a straight line, you have a shorter distance. So what is the curve that will give you the motion that goes from A to B in the shortest time, right? Where the force is only gravity and the motion is determined by the surface that you are traveling on. So this is the problem that can be solved using calculus of variations. And we don't need to go through the details. I can give you the solution. The path, the ideal path is taking the shape of a cycloid. So these are the parametric equation describing this. So this tells how the x and y position of the particle changes over time and is given by this expression. So this is precisely the cycloid. or actually the upside down cycloid. Okay, so this is the solution that was solved if you use calculus of variations or variational principles or things like that, right? And we can actually do an experiment to see that this cycloid is takes the fastest path. So I'm going to show you a video. Okay. So in this experiment, this person will release 3 rolling balls along 3 different paths. So I have a straight line, which is a blue ball. This is the cycloid. This is our answer, the red ball. And this is the yellow ball, is this type of path. So this person will release the 3 balls, and we will see who will arrive the end point first. So who will be the fastest, right? So releasing the balls and let go. Okay, it's very fast, so there's going to be a slow motion replay, right? So they will release the ball, and you see hopefully clearly enough over Teams that the red ball arrives first. So the cycloid really is the path of shortest time, the Brachistochrome. Okay, so yeah, so the path is the cycloid, and I believe most students here have encountered cycloid at least probably in the calculus course. So it is one of the questions in the calculus textbook, right? And hang on. So the cycloid is defined to be this, so we can see this picture, right? So it is a path traced by a point on a circle rolling on a flat surface, right? So you will, it is one of the questions in the calculus textbook, the Stewart textbook, right? So the details are given by here, right? So the parametric equation is given by this. If the sign is positive, then you get the cycloid rolling like this, right? So it is basically a point traced by a point on a circle of radius b rolling on a horizontal surface, right? So I've been emphasizing horizontal because next I will talk about hypocycloids later. But firstly, right, where else do cycloids appear in physics? It appears in electromagnetism. So suppose I have an environment with a uniform electric field, right? So all the electric field are pointing in this direction, and also another uniform magnetic field. So this magnetic field is perpendicular to E. Now, if I have an electric charge, if I put it here and I let it go, right, what is the motion taken by this electric charge? It turns out that it will trace out the shape of the cycloid as well. And the physical reason why is because I have 2 forces. So if I have electric charge, then the electric field will have a force along this direction, and then a magnetic field will exert a velocity-dependent force on a charge, electric charge, and this is the Lorentz force law, right? V cross B times the electric charge. So this force, the magnetic force, is always normal to the velocity, right? V cross B. So it's changing all the time, but the electric force is constant if the electric field is constant. So the interaction between these 2 forces will push the particle to travel in such a direction, right? We can solve this from the Lorentz force equation. And in fact, right, the students who took 107 General Physics 2 with me, we actually done this in chapter 3, and in fact, it was also a quiz question, right? So you might have remembered this before. Okay, so this is where cycloids happen in electromagnetism. So that was cycloids. Now, how about hypocycloid? So cycloid was about a circle rolling on a flat surface. A hypocycloid are circles rolling inside another larger circle. So the small circle is radius b, the larger circle is radius a. And the parametric equations are given by this. So the a and b will determine how the shape of the cycloid looks like in detail, right? So as tau runs, right, so this p will trace out a certain shape. So another important quantity is we will define here to be n. So n is the ratio of the radii of these 2 circles. So n can be any real number. If you put any circle of any size, it will give you some corresponding n. But if n is an integer, you will get these nice perfectly closing loops. So in this case, if n is equal to 3, I get 3 cusps or 3 sharp corners, and it will close exactly. So this n equals to 3 case has a special name. It is called a deltoid. Okay, so if n is equals to 4, I will have 4 cusps or 4 sharp corners, and it also has a special name. It is called an asteroid. So just to see something fun, I show you the animation of how the deltoid and asteroid is traced out. Okay, so yeah, it's just like a circle rolling inside another circle. So for the case, so you need the radius of the smaller circle is 4 times smaller than the larger one. And as it rolls on, you will trace out this asteroid shape. Okay. Yeah. So hypocycloids are also a solution actually to another Brachistochrome problem. But instead of a uniform gravity, we are talking about a Brachistochrome problem that takes place inside the Earth. So when inside the Earth, the gravitational field is a bit different. It has a spherical symmetry, and it arises in the concept of the gravity train. So it is outlined by this paper from 1966, and the concept is the following. So let's say I want to travel between two cities, right? From one point to another point, and instead of flying, the idea is to dig a tunnel from one city to the next. And instead of having to consume fuel or electricity or petrol, right, we just let gravity to accelerate your train, right? So that you don't have to consume any energy. So you just dig a tunnel, and then you just drop whatever things is here and let it accelerate under the Earth's gravity, and it will arrive at the second city. So the terrestrial Brachistochrome problem is where what is the shape of the tunnel that you can dig so that I can arrive from point A to point B in the shortest time. So the answer is the hypocycloid. So a hypocycloid, it will be fastest. So if you dig a tunnel of any different shape, it will take a longer time. Okay. So the reason why I put this movie poster here is that this is one movie where it involves the gravity train inside the story, the remake of the Total Recall. Right. So the original Total Recall has no gravity trains. Okay, so where else in physics do cycloids and hypocycloids occur? So usually they happen when there's the one I was talking about, the interaction between two different forces. So one force is always constant and the other force is velocity dependent. So it happens if you consider a charged particle around a weakly magnetized Schwarzschild black hole. So this is an approximate solution. You solve Einstein gravity and then you put a magnetic field here such that it do not affect the gravity. But if you put a charged particle, there's still a magnetic force, and the second force is the gravitational force. So according to a paper by Frolov and Schum, they have solved this situation. They can encounter the different case. So the case that we are focusing on in today's talk is about and those with the sharp corner. So it's this one in particular. Right, so this was Frolov and Schum in 2010, where it's around a weakly magnetized black hole. So the one where I was mentioning, I read John Bay's Twitter, and it reminded me of something when I was working on it, is when I was doing this paper. So I was solving a problem about the fully magnetized black hole, is the Ernst spacetime, but in one section, I focus on a case where m equals to 0. So there's no black hole in this spacetime, so just magnetic field. So it's the Melvin universe actually, right? But it's just one short section, and then I was just simply looking for orbits with sharp corners. So some fun shapes you can see here is something that looks like an eye. This one looks like a triangle, but this is the one that was very familiar to hypocycloids. And then at that time, I didn't know much about hypocycloids yet, and it just looks the same. So then what we are going to do in the next few chapters is to explore how to calculate and show that it is actually the same. So this one, right? So this is the asteroid. This one, you can say, is like a deformed deltoid, right? Instead of a curve, it's like almost a straight line. So is this really related to the hypocycloid? I will comment on this at the end of the talk, right? Near the conclusion. So now, so I'm about to connect the idea of hypocycloids to the Melvin universe, but in order to do that, the parameters used are not very convenient, right? So it's convenient in the original definitions, but to make contact, instead of describing the family of curves in terms of A and B, I will need to express in terms of R plus and R minus. So R minus is just the minimum distance from the center of the larger circle, and R plus is the maximum distance. So therefore, R plus is just A. Okay. So the ratio N B over A can be expressed in terms of R plus and this. And so from here onwards, we will try to describe the cycloids in terms of these two parameters. And the next thing I need, right, is the following, because just now the equations for the hypocycloid are given in terms of Cartesian coordinates, right, the x and y equations. It will be more convenient later to convert into polar coordinates. And then one next problem I will need is that what I really need is the differential equations that is satisfied by the curve, not the equation itself. So this is kind of an interesting opposite situation, because normally we have a differential equation and then we want to solve it to get the solution. But now with the solution, actually I just want the differential equation. So these are the three important equations describing hypocycloids. We will refer to this a lot later, so try to keep this in mind. This equation is this, right? So I have an equation for r dot. Dot is the derivative with respect to tau, and the equation for phi dot. So it looks like this. And then if I eliminate the parameter tau, right, so I can express everything in terms of r and phi. So this is a differential equation for dr d phi square. And it is, in particular, there's a negative r square here and the r4 times a bunch of constants. So on the right hand side, just a polynomial of degree 4, right? And these are the bunch of constants. Okay, so these three equations, the equation for r dot, phi dot, and dr d phi, right? So they will describe the curve. So I'm gonna keep this equation aside, and we will come back to this later. But so far, all these are the important features of the hypocycloids that I will use later. Okay, so what time is it now? Okay, so yeah, so next I will talk about the charged particle in the Melvin spacetime. So what do I mean when I say the Melvin spacetime? So the Melvin spacetime is just the empty spacetime, so there's no black holes anywhere. All I have here is just the magnetic field, right? So a Melvin spacetime is describing a situation where I only have a magnetic field pointing along the z direction, and the configuration is cylindrically symmetric. So I have the gauge potential over here, right? And having a gauge potential, if I take the derivative, I can calculate the field. And this field has no electric component. It only has magnetic. So yeah, so once you take the derivative, it will give you the vector along the z direction. So this B here is a scalar that will parametrize the strength of my magnetic field. So if B is a large number, it means that we have a very strong magnetic field. So if B is small, it's a very weak. If B goes to 0, I have 0 field. Okay, so this will give us the magnetic field on this situation. And as you have known, right, and also for students, we learn from relativity and things like that is that E is equals to mc squared. And m is mass, so mass is a source of gravity, right? Now, over here, right, I have no mass, no black hole, nothing, but I do have a magnetic field. So this magnetic field, well, if you learn electromagnetism, magnetic field stores energy, right? So there's energy. And then we have energy, and Einstein's formula said energy is equal to mc squared. So it has a mass as well. So what I'm trying to say is the magnetic field itself is a source of gravity, and it will cause a gravitational attraction, right? It will cause a gravitational attraction. This is why the space-time metric is not flat, right? It is distorted by this lambda function. The lambda is given by this function over here. Okay, so as you can see, right, if B is non-zero, it will deform the space-time. And the gravity, although it's hard to read off from the metric, the gravity is attracting particles towards the center of the universe. So that is the Melvin space-time. Exactly, yes, correct. So that is what I was trying to drive at, right? So I have two forces, one magnetic force and one gravitational force. Yes. Yeah. So this solution has only one parameter B, and if B goes to 0, lambda is 1, then we come back to the flat Minkowski space, right? So this is a pretty simple solution discovered by Melvin in 1964. But there's an interesting story behind why they were looking for this solution at the time, and it's something to do with John Wheeler, and at that time he was developing a theory of electromagnetic geons and things like that. So along the way, this was a shoot-off or a spin-off solution from that research. So that original geon research was no longer popular today anymore, but we are still working with this one now. Okay, so yes, essentially this solution describes a cylindrically symmetric bundle of magnetic field lines held together by its own gravitational field, right? And what we want to explore today is how a charged particle moves inside this field. So Qinghao has exactly described it nicely already, right? So I have gravity and I have magnetic field. The magnetic field pointing in the z direction. The gravity is attracting everybody towards the center, the axis. So I have two. So if the charged particle will experience two different forces: the gravity force in the radial direction, and also the v cross b, right? So the velocity dependent force. So this is the reason why particles can be pushed to move in the hypocycloid types of motion that I am looking for. So that is sort of the general intuition, but to establish the to describe this more precisely, I need to derive the equations of motion for the charged particle. So if I put a test particle, the mass is very small, but I have a charge E, which can be large, moving in this space-time. And for this particle, it will the Lagrangian of this motion is described by this, right? So this is the Lagrangian of this motion, and actually Lagrangian is kind of another Brachistochrome problem, calculus of variation. So this part here is due to the force of gravity. So the gravity will make the particle move according to this term, and this term here is the magnetic force. So it depends on the interaction between E times B, right? So if any one of them is zero, then I have no magnetic force, just gravity over here. And because this space-time, right, the Melvin universe has a lot of symmetry. So it has symmetry in the time, angular, and z direction. And because of this symmetry, we have three constants of motion. So I have a conservation of energy because of the time, and conservation of angular momentum because of the phi killing vector, and conservation of linear momentum in the z direction. So this will cut down our equations of motion. Thanks to these three constants of motion, three of my equations of motion are just first order, so which are easy to solve. So these are the equations for how the t, z, and phi evolve according to some parameter tau, which is usually the proper time. And then for the r motion, right, so we can derive the equation of motion for the radial direction by applying the Euler-Lagrange equation. So I get a second order differential equation, which is a bit messy and hard to solve, but we can always solve this one using numerical methods. So this one is no big deal, right? So essentially, these four sets of equations will completely determine how a particle moves inside the Melvin universe. So, but then on the other hand, right, this equation is a bit messy. Although we can solve it numerically, it's hard to extract any intuitive information. What we really want is some analytical solutions, right? Whether it's approximate or not. So to do that, we can actually get a first order equation for r, because a charged particle will have invariance in the velocity 4 vector, right? So if I put in the expressions from the previous slides, energy and things like that, then I'm able to obtain a first order equation for r. So r squared, and so the r squared is given by this equation. So this is something similar, something has the appearance of a conservation of energy equation from Newtonian mechanics. So r dot square is something like a kinetic energy term, and then this is a constant, and then I have a function of r. So this one you can treat this like a potential energy equation, right? So this is a useful equation that will tell us a lot of some physical properties of the motion. So the effective potential is given in terms of the lambda function and all this interaction, and also it depends on the angular momentum. So what time is it now? Okay. Yeah. By the way, right. So the space-time is symmetric in the z direction, and actually, right, the p here is actually not important. So the momentum along the z direction is not important. Even if it's non-zero, right, you can do a Lorentz transformation onto your coordinate system such that I'm in a frame where I have zero momentum. So we won't lose any generality if we set p equals to 0. So if I collect all the important equations here, again, I have three equations. I have equation for r dot, equation for phi dot, and an equation for dr d phi, right? Just now, also remember, for hypocycloid, I have r dot, phi dot, dr d phi. So I'm going to compare these two. But at the moment, right now, in the most general case, they are totally different, right? So just totally different and highly nonlinear and not easy to solve. Although we can always solve it using numerical methods. So these are the three equations of motion that we'll be dealing with a lot in the next few slides. So let us begin analyzing some general behaviors of the solution. So let us look at the R motion first. Okay, so the R motion, as I said, right, is kind of like the potential energy equation. So total energy minus potential is something like kinetic energy, right, up to some prefactors. So this will tell us the range of the particle, the range of movement of the particle, because, right, this is R dot square. So R dot must be a real number. It's just some velocity value. So it must be a real number. Therefore, the valid motion of R should be in the region where the potential is less than E. So if I have a E, whatever number it is a some constant number, then the potential energy must be smaller. So in this domain, between R minus to R positive, this is where I can get a real number for velocity, right? And in particular, when the particle is at R minus, the minimum distance from the center, then R dot becomes 0 over here because these two are equal, right? And then when I come into here, the R dot is the highest, and then I come back here, R dot is 0 again. So this is the reason why it's very similar to your Newtonian mechanics equation, right? So R dot is 0 at the endpoints, R plus and R minus. Okay, so if you change the energy, you just change the domain accordingly, and if you change the angular momentum, because the effective potential will change the shape of the graph, so it will also change accordingly. But essentially, there's always some R plus and R minus over here. Okay, so that's for the R motion. Now for the Phi motion, what happens with the Phi motion? That's very interesting if you look at this equation. Oh yeah, by the way, I forgot to say that all the quantities here, without loss of generality, we will consider all of them to be positive. Because if any one of them is the opposite sign, you can always change your coordinate axis. You flip it the other way, you always get it back, right? So everyone is positive here. So the phi dot equation is, phi dot is the angular velocity, right? The angular motion over time. And the phi dot, according to this equation, is a difference of two positive terms. So as R changes, right, there's a chance where phi dot can go from positive to 0 to negative. So the point where it becomes 0, I will define as a special radius R star, and I just need to solve this equation for R. This is the expression for R star. So this is where R phi dot becomes 0, right? So phi dot can go anywhere from positive to 0 to negative. So if it changes from positive to negative, then right, so it changed to negative, and then maybe it will change to positive again. Okay, so these are the important feature I want for the phi dot motion. Okay, so now so as I'm saying, right, this whole talk is I want to look for hypocycloids. So hypocycloids are the motion with the sharp corners, with the sharp cusp, and the sharp cusp will happen when R dot and phi dot are 0 simultaneously. Okay, so that is the situation I'm looking for, and I've said I found the R star, which will make phi dot become 0. And earlier, if you recall, R plus is where R dot becomes 0. So when these two numbers are equal, right, when they're equal, then R dot and phi dot will become 0 simultaneously. And this is the situation where it will give me the sharp corners. So from here, I can fix the energy, and then I can calculate all the relevant quantities to produce this type of motion. Okay. So let's see some examples. This is by solving the second order equation numerically. So for any initial angular momentum and any energy and the charge and magnetic field strength of a space-time, I can put a charge there and release it and see what happens. So if R star is equal to R plus, right, it will go according to this, and then these two are where R dot, R phi dot becomes 0 simultaneously. So you get the sharp corners as it goes along, right? So, and in the general case, the orbits do not close perfectly, but it will just continue giving you more and more sharp corners. So if R star is less than R plus, what happens? So this one is also interesting because R star is within R plus. So that means phi dot will change sign before it reaches maximum radius. So as the particles goes, right, before it arrives at the maximum radius, it will change direction at r star. So it will go backwards for a while, then I reach the maximum distance, and then come down again, change back direction to forward, and keep on continuing. So this, I can create loops along this motion, although I won't be focusing on this. And then a slightly more boring situation is where r star is greater than r plus. So when r star is outside the valid domain of motion, then the phi dot will not go to 0. So it's always positive, so it doesn't change direction. Yes, Trachoid is what I'm talking about here. Yeah. So there's a parameter lah. A Trachoid is parameterized by some number. So when the parameter is 1, I get the cycloid. And then Trachoid, this one is the prolate cycloid and the curtate cycloid. Yeah, those things. Yeah. So the Frolov paper was the cases of the Trachoids. Okay. Any other questions now? Yeah, so by the way, right, the PHY student, yeah, you can't type in the chat, but if you have a question, you can talk to me on the microphone. So whoever is outside my organization, yeah, Tichi or anyone. Okay, so let's go back. Okay, so let's go to, so let's actually find the hypocycloids, how to get the hypocycloids in the Melvin universe. So firstly, right, a simple solution to the equations of motion is just r constant. So when you have r constant, right, then you can easily solve the r equation. And then if you choose your angular momentum and energy to take this number, you can satisfy all the other equations as well. So that will give us a valid solution, although it's kind of trivial. It's just r constant. So that means the particle is just traveling at a circle, constant distance from the axis always, right? So these are just circles of radius r0. And if you can choose a radius that you want and choose the charge and b, you can put all these numbers, you can produce the desired motion, right? The circular motion. So, so that is boring. So we want to look for more interesting types of motion. But for more interesting type of motion, the equations of motion, as you have seen earlier, right, they are very complicated and difficult to solve. So let us try some approximations. So what we are going to do is to perturb about the circular orbits and try to find new solutions based on that. So which is to say that I'm going to write the r coordinate of the particle to be the circular orbit plus a small perturbation, and then I will find a solution for r1. Okay, so here I will treat epsilon to be a very small number. So if I put this into my equation of motion and only keep the leading orders of epsilon, then which is to say I'm linearizing the equations of motion. So I got this simplified set of equation. Okay, so the equation for r second order is just the harmonic oscillator equation, right? If you up to order of epsilon square and beyond, right? So this is just a harmonic oscillator equation. So the solution is just sine and cosine. So easy to solve. So once we solve this, I can put the linearized equation for phi, just put this in and then integrate it directly, right? So we can find new solutions in this way. The omega here, beta and beta 1 here, these are just constants. Although I do not show you the formula, these are just rational functions of these quantities. Although it's a bit messy and complicated, so it doesn't really show much by showing the expression. So these are just functions, right? These are constants. Okay, so these are constants. But once we solve this, right, then this is the solution. So as you can realize, or maybe some of you have already recognized, that this solution is the equation for the Trachoid, as Qinghao has shared in the Wikipedia link. So these are equations for a Trachoid in polar coordinates. So the Trachoid is parametrized by the parameter zeta. In the context of my charged particle here, zeta is beta 0, beta 1 times epsilon, right? So this is the first order term. So it's perturbing about the constant, it's a perturbation about the constant circular motion, right? So yeah, so these are the, this describes equations of a cycloid. If I'm looking specifically for cycloid, then I need to choose the parameter to give me 1 over here. But in general, zeta can be any number, right? So when zeta, I believe if zeta is greater than 1, you get the looping shapes, the prolate cycloids. But if zeta is equals to 1, you get a sharp corner, and less than 1, this is where phi dot never changes sign. So when they never change sign, so you just get this kind of boring type of motion. So this was obtained by Frolov and Schum when they were studying charged particles around a weakly magnetized Schwarzschild black hole. Okay, so from that we can get some other general information. For example, right, as the perturbed circular orbit goes around one round, I can count the number of cusps by just dividing the radial frequency over the angular frequency. So this gives us an estimate. Remember, it's estimate because remember our equation is a linearized approximation. So, but it's given by a simple formula omega over beta. So let's see some examples. Okay, so if I do it for the case of the charged particles in the Melvin spacetime, right? Let's say I start with a perturbation around a circular orbit of radius 6. So let's start with a circle of radius 6, right? And then I perturb the charge, so it will oscillate around the R6 region. And then if I choose the magnetic field and charge to have a certain value, then such that I get a zeta that's closest to 1 as I can get. So this is really the result of the numerical solution, which agrees with the perturbative solution. And for this case, right, as you can see, the zeta here, if I plug in the values into the formula, it will give you 1.09. It is close to 1, but not exactly. So these are, technically speaking, not the perfect sharp corners, right? So, but it's close enough that on this scale, it looks more or less like a cycloid. Okay. Then as it goes along, right, using the formula from the previous slide, I can put in the values, and you can see that the number of cusps around one full circle is going to be 500. So this is a circle of radius 6. It will go 500. It will give you 500 sharp corners before it comes back to the starting point. Okay. So yeah. So this is the perturbed circular orbit if you disturb the circle of radius 6 for this case. So the epsilon here I choose is kind of a large number actually to be comfortable, but this was the number that's large enough to give a visual look that is more obvious when you plot it on the graph. Okay, wow, I'm talking faster than expected. Does anyone have any question? No question. Okay, so
you have a gravity and you have a magnetic field.
Right.
Is it possible that if you have like these two forces working together in different direction, then you can have like something else, some more interesting curves, maybe?
Yes, actually. So yeah, it's one of the things I potentially consider to work on. For if I have a black hole with a magnetic charge, right? So that's a chance to use my visualizer. Okay. Yes. Yeah. So the Melvin universe is where my magnetic field are all pointing in this direction, and the gravity is pointing here. But you can have a black hole with a magnetic charge. So I have a black hole, and then it's a magnetic monopole charge. So it is a radially symmetric magnetic field. Okay. So you can consider a motion of a particle over here. So if I have a charged particle E and going at some velocity V, then it will have another like non-trivial interaction between these two. So it's possible if you can find a space-time that is
okay.
have these two effects. Yeah. Anyone else? Any other question? Okay. So if not, let us go to this part. By the way, everyone can still hear me, right? Yes. Usually something wrong happens if I switch between mediums. Okay, good. So let's talk about the last part, and it is the more interesting part. The least non-trivial part is this one. The hypocycloid in the weakly magnetized universe. Okay, so actually, why do we consider weak magnetization? Again, right, as you can see, the earlier equations of motion is very complicated, so we want to solve it, and we want to find a solution, at least to find a situation where we can solve it, we have considered some parameter to be small, so we can neglect some terms, and at least we can find some solution there and understand the physics in that situation, right? So this is why we consider a universe with a weak magnetic field, and also why Frolov and Schum consider a weakly magnetized structural solution. The equations are simple like this. So what I want is to solve the equation where the magnetic field is weak. But then, right, the magnetic field is the source of, simultaneously the source of the magnetic strength and also the gravity. So if I turn them down to be small, right, then these two effects will be small as well. So I'm kind of having like two contradicting requirements over here. I want to weaken my magnetic field, but I also want the hypocycloid motion, right? So the hypocycloid motion, the interesting part comes from the interaction between the electric charge and the magnetic field. It will give you a velocity dependent force. So I want to weaken my magnetic field, but I still want the force there. So in order to satisfy both conditions, right, if I turn down the field, I need to increase the charge at the same time, so I can still have the relevant situation that I want. So this is the reason why we are going to do an expansion of my equations of motion in a parameter lambda. So if I rewrite my magnetic field to be g lambda square, right, and then I take lambda to be small, so this term will be small, and at the same time I express E as q over lambda. So as lambda small, this E will become large, okay, and then g and q are constants, some other constants which can be large or small. It will gonna be depend on what I need later. But essentially what I'm about to do is I'm going to take these two expressions, put them into my equations of motion, and then I do an expansion around small lambda. So up to leading order, my three equations of motion, the r dot equation, the phi dot equation, the r d phi equation, up to the leading order, they got this. So all these are the higher order corrections. And then, yeah, so I got the equation for r, phi, and theta. And if you look closely, right, although it's complicated, but most of them are constants. And these are actually precisely the same equations for the hypocycloids, just that the constants have different names. So they are identical. And to see this, right, I guess the easiest example to see is, let's look at equation 21. So up to leading order, right? So that means up to leading order, which means this equation is true as long as the magnetic field is strong enough, weak enough, and the charge is strong enough. The dr d phi square is equals to a negative r square, and then r4 times a bunch of constants, right? So this is like the hypocycloid. If you remember, the hypocycloid equation is dr d phi is negative r square, r4 times a bunch of constants. So I guess we have answered the question that arise when we looked at John Bay's when I saw John Bay's Twitter account. Are they the same or not? And yeah, so they are the same in the regime where the magnetic field is weak. Okay, so this is the second situation where the hypocycloid happens. Yeah, so okay, any question? Oh, thanks, Gloria. You dug it out. Yeah, so I tagged, after I published this paper, I tagged him, and then he replied, and yeah. So what was I? Yeah. So the next thing I forgot to say is the next result is even more interesting, and I did not expect the following result. Is okay. I have these two equations. They are almost identical. The constants are different. So the natural thing to do is to compare the constants, and these are the results. Okay. So the constants is this. So if I compare the two equations, right, then I will get this expression. So the hypocycloid is in terms of n, and then this is the parameters, and this it is an equation for lambda over q. Now recall that I actually define E to be q over lambda. So this is actually 1 over E squared. So if I solve for E, I get this equation over here. And this is kind of interesting equation is that now, right, I can actually get an equation to produce whatever shape of cycloid that I want. So remember that n is if it's an integer, it will give you the number of corners. So if I want a certain number of corners, I put this n into here. Let's say n equals to 3 for the deltoid. Then it will give me the necessary charge in order for the particle to travel in this way, right? So for different n, I will get different types of motion. So yeah, so this is to me at least, this is a remarkable result, because on the right hand side, right, I have n. These are just the properties of some mathematical curves. Then on the left hand side, it gives you the physical charge. So this will give you, yeah, giving us the relation between the charge and the number of cusps. So let's try to see and use this equation over here. So yeah, so if the lowest integer of n, right, if I put n equals to 2, you just get e equals to 0. So, and then if I put into my numerical code and let the particle run, I just get a straight line, which is perfectly expected because this is a zero charge, it's a neutral particle, so there's it's not affected by the magnetic force. So it's only affected due to gravity, and the potential due to gravity is just a potential well. So the particle is just oscillating between the potential well. So that is pretty straightforward. If I want n equals to 3, I put this into the equation. The charge that it gives, that you need, turns out to be half. So if I put a particle of charge half into the simulation and run the code, right, I do get the shape of the deltoid. And then, yeah, so n equals to 4, right, I will get the asteroid. This is the charge that you need. If I put in n equals to 5, it will give me this charge. And if I run the code, I will get this shape. And I don't believe this has a special name. I don't think, right? It's up to asteroid only. So what time is it now? Okay, almost just within time. Now, the triangle thing for my earlier paper, what is it about? So it turns out, right, remember, actually, the equation that I derived, right, all these are for a weak magnetic field. So if I increase back the strength of B again, then all these descriptions are no longer accurate, but I still have I can still solve it numerically. So if I increase the magnetic field, right, I can see what happens to the trajectories, to see what happens. Even though I no longer have the analytical expressions, I can see the numerical solution. So it turns out like this. So when the magnetic field is small, I get the hypocycloid shape. And then if I increase the strength of B, then the shape will deform, right? So I increase it some more and more, the shape will deform outwards. So this particular one here that is almost a straight line was like the triangle that I got in the earlier paper. So that kind of addressed another outstanding issue that we had. Then if I increase all the way more, increase higher and higher, then I get a particle that is almost like a circle, but not quite. So this is actually the perturbed circular orbit. So that means we have a family of curves connecting the two regimes. So on the weak field regime, I get a hypocycloid. And in the previous section, when we're looking at the perturbative circular orbit, then I have another situation with a cycloid as well, right? So essentially, which is to say that I would say that this is numerical evidence that there exists a family of curves. If I increase the B, I go from one extreme to the other extreme, right? So you can do it for n equals to 3, n equals to 4, and so on and so forth, right? You'll get something similar all the time. Okay, so yeah, so let's conclude. So what we have found is that, yeah, I answered the question that was bugging me after when I was reading the John Bayes' Twitter. And hypocycloids do occur in the Melvin universe in two regimes. And this is the one of my favorite formulas I got out of this. So, but actually, right, if you notice, for a research talk, everything I talk about here is actually kind of simple, right? The worst thing I did is just nothing sophisticated, right? All I did was expanding the equation and then compare the parameters, right? So nothing sophisticated, which is why I'm not able to address this problem. Like, why is there hypocycloid in this magnetic field in the first place? Although physically we know, right, it's the interaction of the two forces. That is sort of like a rough idea. But usually in physics, when we encounter something simple or something symmetrical or elegant, some mathematical object in a physical solution, it is usually because there is some symmetry in the system. So yeah, so hidden symmetries in physical systems have been found in that way. So which which brings us to the question: why is there hypocycloids in this, or is there a more accurate mathematical description of this general family? So I don't know the answer to this. Although one clue or one possible starting point to investigate, it probably come from this paper. According to this paper, right, if you plot out the trace of the eigenvalues of SUN, right, if you plot them out on a complex plane, they all lie in the domain will lie inside some hypocycloids. And actually, in fact, I asked Ching Hao about this last time, if you remember. I was asking you about eigenvalues and trace of SUN. So I don't know whether it will shed any light to this issue. So I guess friends in math will have a better answer to this, or you can tell me, or in fact, whether I'm asking a stupid question. I don't know. So
yeah, I don't really know about that.
oh, okay, yeah, thanks. So but at least there's some starting point. But aside from that, because what I did was actually, again, like everything is very simple, so it's easy to extend in multiple directions. For example, right, I have been focusing on all the case with sharp corners, r plus equals to r minus, and yeah, Ching Hao has pointed out that when they are not equal, these are trochoid. So actually, one should generalize and see whether you can get more generally hypotrochoid motions in this space-time. So again, right, this project is not difficult. It can be a Europe's project or a FYP project. So if any student wants to do, let me know. Hopefully.
I think it's also possible that because like the magnetic field is more flexible than the gravity field, right? Gravity field is like you need center of mass, but like magnetic fields are more flexible. So maybe you can play with these two forces working together and then generate some other different trajectory. I think that might be possible.
Yeah. So yeah, so I think, for example, this type of situation. Yeah, so you're right, like the gravitational field is either spherically symmetric or cylindrically symmetric, because otherwise it's almost impossible to solve. So yes, one thing we can consider is to play around. Even if we can't solve the Einstein-Maxwell equation, we can consider like Frolov and Schum. They consider a weak magnetic field. So as long as you can claim it's weak, then you do not need to worry about the Einstein equation side. So you can put in whatever field that you want, as long as you solve Maxwell equation. And solving Maxwell equation is much easier than solving Einstein's equation. That's true. So yeah, that's another possible extension. So yeah, who wants to do FYP? In fact, I posted this as the FYP, but nobody wants this project for this semester. But other than that, I guess that's all from me. Yeah, so thanks everyone. Yeah, let me know if you have any question. Thank you for your time.
Okay, thank you very much, Yen-Kheng. Are there any questions?
Yes, I have a question.
Okay, please.
Yes, hi, Muni.
Just ask the question.
Oh, it's here. My last picture, I get a flat triangle. So is this deformation defined by some function where the time corresponds to a physical point is convex and non-convex? So yes, yeah. So this family of curves, well, for one thing, these are obtained as numerical solutions, but these different curves are obtained by changing the B. So I would expect this is a function of the magnetic field strength. So yeah, although the exact critical point where it becomes convex to concave, I guess we can't really tell because they are numerical solutions. We can look at it like visually and look at the numerical data, but if we can find a way to solve the equations of motion, at least approximately, then maybe we can extract some information about this. Is it related to what you're talking about?
Munir?
So I guess the critical value will be some critical value of the magnetic field strength. So if I change the field strength, then but my guess is also it might be a product of B times E also actually, because you need to fine tune the charge to get the sharp corners as well. So it will be a function of E and B. Yeah, I think so.
Are there further questions?
Yes, sir.
Yes.
So like the in the I think in the last part that you say that there was a weak field, like magnetic field.
Yeah.
So can we know its direction?
It's still in the Z direction. Yeah.
Yeah, so it's just like
Correct.
vertical
So,
with the.
yeah. So let's say this is like so my weak magnetic field is a vector, right? So it has a magnitude and the direction. So in the section I was talking about is I keep the direction the same, so it's always in the Z direction, but the weak field means this number is small.
Yeah, it's just still fuzzy about, I mean, like how to know the relatives between the directions.
So yeah, so in my Melvin universe, right, because there's not, so everything is cylindrically symmetric, so everyone is pointing in the Z direction. So if I got X, Y, and Z, so my magnetic field only has the vertical component. Okay, and then my charged particle is at a Z equals to 0, so it's at a horizontal plane. So so let's say if a particle is going in a circular orbit, then it is going like this.
Maybe you can think it this way. In the beginning, the first cycloid example, that if the compared to the gravity, if your initial velocity is like very, very fast, then the trajectory will looks more like more flat, right? More like a straight line. But like if the initial speed is very slow, then it tends to be more convex.
Right. So yeah, so in this, like the electromagnetism case, right? So I got this B, right? So yeah, so if the initial velocity is slow, right? So this is the velocity here. So the force experienced by this particle is E, and then E plus B cross B. So if this is initially very small, then the magnetic force is weak. So you mostly have this electric field force, so you more towards this. But if you accelerate more, then V will grow. Then the magnetic field will start to play a role. So it will curve the particle.
So it's just like the vertical with the plate, right? Or
But yeah, so everything is on the, well, here is horizontal plane. Yeah, the horizontal plane. So in this picture, right, yeah, come to think, I should have said in the beginning, like for pictures like this, so the picture like this, the magnetic field is coming out of the picture, perpendicular to this plane. So it's coming out of the paper like this. So the axis of symmetry is at the center, and then the phi is this angular direction. So this is the x and y coordinate. So the z coordinate will come out to the surface. Got a question?
Any further questions?
So yeah, I answered everyone's question, right?
yeah.
We have already had several questions. Do there also cases occur where we do have an infinite number of cusps? So if the n becomes an irrational number?
Yeah, so if n, okay, so there are a few cases I did not describe. So if n is a rational number, they are finite. So it will go a few rounds until it closes back to the initial point. So that happens if n is a rational number. But if n is irrational, then eventually, yeah, it will have infinite number of cusps, and if you run the time forward, eventually it will fill up the entire circle.
Then I have another question about the cusps here. What about the tangent? Here the tangent is perpendicular to the radius, or is parallel to the radius, right? It's perpendicular to the circumference, right? Or is there a finite angle between...
You mean the tangent at which point?
Yes, here the tangents. Here are the tangents here parallel at where they hit the radius.
Right,
here
right.
The tangents, are they here at the cusps? Are the tangents parallel at the cusps for the two, or do the tangents have a finite angle here?
The tangents are undefined, right? Because phi dot and r dot are 0 simultaneously.
Well, you should be able to somehow find the limit, right?
Oh, that's true. So, but these are properties of hypocycloid, which I'm not familiar. Yeah, so.
Okay.
I think the tangent depends on the initial velocity and the field, the straight of the field, right?
Yeah, so in practice, all the code I got here is like I start with 0 initial velocity, so r dot 0 here, and then I let it go, and it will just start moving under the pull of gravity and the magnetic field, like this.
Okay.
So okay, so I guess that's the So I guess the velocity, the tangent vector here in the limit of the cusp, it will be 0.
Okay.
It will be 0. Yeah.
You had later on, you had some pictures where this one looked more, yes, as if there were a finite angle. So, for instance, here apparently, I don't see, or here in the triangle, this looks very much like a triangle. Do we also have the cusps here?
Yes. So these are like very rough numerical solution, but yeah, these are where r star equals to r plus. So these are the cusps. But they are not.
The angle is not like 60 degrees as we see it here, but rather also more or less.
Yeah, they are not perfectly straight actually. There's some it's slightly curved near the cut. Yeah. So let's see if I can zoom in. Yeah. So it's slightly curved at the edges.
Okay.
Yeah. So, but I don't know why. So this is the case. This is the section of the paper which I did not investigate very closely, just like showing examples of numerical solutions. But these are like more interesting case.
So there's no straight line case, or
straight line case, yeah. So when the charge is 0.
Only when charge is 0 that can get straight line case.
Right.
Yeah.
Because then the magnetic field will not affect. So when the magnetic field force is present, then it will push the particle somewhere else.
Does the straight line case correspond to this I-shaped curve with the two cusps you had in the previous picture?
No, I don't. No, because well, for the I-shaped cusp, definitely the charge is non-zero.
So it's.
Well, I was thinking, if you make the charge here 0, would it collapse to the straight line?
Yes. Yes, it will. Oh, that's what you meant. Yeah.
Yes.
So
yes, for me that looks like an eye, right?
Right. So
like
I guess.
Human eye.
Yeah, it does look like a human eye. So this corresponds to the analog of for n equals to 2. Yeah. So if you can imagine, right, if I start with a straight line, so straight line with a weak field, and if I increase the charge, I can't find it. Where is it? If I increase the charge, then the straight line will open up, like it will open the eye, like this. So yeah, I believe that's the case. Although again, I did not investigate this very thoroughly.
Okay, thank you. Then I want to make just one final comment. I very much liked your perfect pronunciation of Johann Bernoulli. This was really perfectly pronounced.
Oh, thanks.
Like a German, so or a German speaking and German native speaker.
Oh, thank you.
Okay. Then Darren has put on his camera. Darren, do you want to make a comment? Okay. So.
Good point. I guess
next week there will be no seminar because we have a holiday. And the next seminar will be on the 18th of December. Is there an undergraduate seminar on the 18th of December?
Yes, Prof. Teo is giving an undergrad seminar for that day.
Okay.
Yeah. No title yet. Yeah, but I don't know what's going on. But she's giving one.
Okay.
Yeah. Not yet. Yeah.
So then, I wish you a nice weekend, and or maybe we meet in 2 weeks for a talk by Professor Teo.
Okay. Okay, thank you everyone. See you guys soon. And thanks for coming. Goodbye.
Do you stop the recording, or can I stop the recording?
Oh, okay, I can do it.
I think anyone can do it. Even I can do it. Like, even